So welcome everyone to the prediction modeling and machine learning seminars hosted by the prediction modeling group here at Biostatistics and Health Informatics at King's College London. We are very happy to have all of you here. As I was telling before, this is our first seminar of the year. We are expected to be scheduling one monthly. The 2 first months of the year were quite busy and we couldn't do it, but from now we promise that we will be here at least until September. We have everything confirmed. So we really would like to see you here every month and enjoying these fantastic speakers and seminars that I think that we present and we try to put forward here. So today I'm very happy to be hosting this talk in which we invited Dr. Nick Cummins. He's a lecturer on artificial intelligence here in our department, at the BHI department, and in speech analysis. And yeah, he's a brilliant researcher and lecturer, and we are very, very, very lucky having him here with us today. He's going to be discussing on the ethical concerns of the AI-based systems and implementations. I think that this is super timely, super interesting, and that all of us developing models that we would like at some point to be implemented in the healthcare system, should we be reflecting at some point about all of this? It's not just developing models and trying that someone use them at any price. We need to understand very well what are the ethical concerns and challenges behind them, and this is why I wanted to reflect about this with an expert in the field, which is how is Nick. So the talk will be as always. So first we will have the talk, then after that you'll be able to do questions to the speakers, and we will start the discussion. You can do that by raising your hand or typing in the chat. I'm happy to read this for you. And yeah, I think that's everything. Remember that this is going to be recorded. It's already being recorded, and you have the transcription as well if you would like to read it or you prefer it. And I think that's it. So thanks very much, Nick, for accepting the invitation.
Thanks,
and I leave it to you. Thank you.
Let me just get set up. So hopefully everyone should see my screen now.
Yes, we can.
Perfect. So thanks. And yeah, today I've titled this talk Artificial Intelligence Challenges and Ethical Concerns. And of course, given my position and the group that I'm talking to, we're going to put a bit of a medical sort of healthcare focus on this. So Raquel's already done a great job introducing me, so I'll skip this slide and sort of go straight to what we're going to cover in the presentation. So before we sort of talk about concerns, ethics, problems with AI, I think it's first best that we actually talk about what AI is, what it means, how does it work in practice, not just in sort of sci-fi or in things like this, but how and what are the limits of this, and then really use this then to sort of focus our discussion sort of in and around sort of current ethical concerns and looking forward to those sort of next steps. So given that, we'll start by discussing what AI is, and any discussion on this needs to start on, well, what's intelligence? And we sort of hit our first problem. There's no really universal agreed on definition of intelligence. So as you can sort of already see already, what is AI is sort of going to be hard to define. We can't even define one of the terms in it. But intelligence is some sort of combination of autonomous and adaptive. No need for constant instructions, autonomous, and being able to change behavior in environment as our problems-based sort of changes, adaptive around it. And the core element to intelligence is, of course, data. Consuming data, processing data, making decisions on data. That's what we do as humans. That's what we hope the AI agents can do as machines. So as I've said, as intelligence is hard to define, AI is hard to define. We want to develop machines here that behave as if they were intelligent. They think and act more like humans, or they're doing things better than we're doing them. So there's all these sort of definitions there, sort of some sort of synthetic artificial intelligence system that exhibits general intelligent behavior. And most AI systems provide an AI-like value and utility in that they essentially help us to solve hard problems. And that's what we're really looking at with AI is it easier just to solve some things with a computer? And in a lot of circumstances, yes, it is. And we'll dig more into that sort of comment as we go along a bit further. So, of course, one definition of AI starts from systems that think humanly. The challenge with AI systems based around this sort of train of thought is that we actually need to understand how humans think. And we need to understand the human brain through introspective, through psychological experiments. This in itself is cognitive science, and that's sort of where AI systems that can think humanly sort of live at the moment, more cognitive science, more sort of thought experiments. We, of course, want AI systems that can act humanly in some circumstances. So displaying intelligent-like behavior, achieving human-level performance in cognitive tasks. And of course, this is achieved by the Turing test, the more famous way of deciphering if something's an AI agent or not. So in the original Turing test, it sort of said if a human integrator, after posing written questions, cannot tell if the written response came from a person or a computer, then the system passes this test. It's fooled the human into thinking it's displaying some form of intelligent behavior. And of course, with the written Turing test, we need to understand natural language processing, knowledge representations, reasoning, and of course, using machine learning, adapting to new circumstances. So there's a lot of different forms of AI happening within that just to pass the test. Then if we want it to actually have some form of perception with it, so not just being written, we might need speech processing systems, speech synthesis systems for a more natural interface than writing, computer vision systems to help it perceive objects, robotics to help manipulate objects around it. So again, we need to add in more sort of various forms of AI with that. Another train of thought around AI is systems that can think rationally. So building systems that do the right thinking when we're trying to create intelligent. And this is irrefutable reasoning using logic, law of thought. And essentially achieving AI like this is infeasible because not all knowledge can be expressed through logic notations. And there are so many ways, so many reasoning steps that can be tested, ways to receive this. It's just a real computational blow up. So we've sort of gone through a few different things, acting humanly, thinking rationally, and sort of discuss some of the limitations around there. But AI really, state of the art now, is focused around systems that can act rationally. So creating intelligent systems that maximize their chances of achieving a goal given available information. This is feasible because rationality defined this way is quite general, and would essentially want to build an agent that can perceive its environment, as we sort of said, take in data, process data, and come up with the best possible outcome it can come up with, given how we've programmed it, given the knowledge that we've sort of allowed the system to achieve or built into the system. And especially in the face of uncertainty, we want the best expected outcome, not the best outcome, the best expected one. There's a slight sort of difference through there. The goals of this is, you know, bigger, longer term, systems that operate autonomously, perceiving environments, persisting over a long time, adapting to change, creating and pursuing its own goals, and again, achieving this best expected outcome. That's the goal of a rational agent. And this is sort of where a lot of AI reading is focused, a lot of AI thought is focused in and around rational agents. And of course, to drive a rational agent, we need data, and we need essentially lots of it. And data is the core to any AI system. With incorrect choice of data, poorly represented data, missing data, AI algorithms will not perform as well as they can. So the outcome is only as good as the data we provide it. And creating meaningful insights to answer questions based on data is creating new information, creating new knowledge. And this is what we're stimulating through AI algorithms. It's not just the data, it's not just the action, but also the knowledge that we gain in creating the algorithms to use this, to transform data, to enable us to use data in different forms, help us make medical or healthcare conditions, and we'll get onto that soon. So yeah, data is king. And When we're thinking more contemporary AIs like deep learning systems, data is really, really king. We've got not that many rules in sort of AI and machine learning in terms of how much data, things like this, but a few rules that we do have are there's no data like more data, and garbage in, garbage out. So if we've got small, badly organized data sets, our AI agent is not going to be good. So we've got this rule that there's no data like more high quality data. So data quality, data quantity are massive issues in this space. And we'll talk about that with the challenges. Pardon me. So we've spoken a little bit about what AI is, and we've gone down this sort of path of rational agents. We've spoken about data, but what can we do? What are some problems that we actually use and solve with AI currently? So first up, search algorithms. This is a big path. Finding a possible goal through multiple possibles of situations. Like the essential thing with this is graph searching or solving a maze, but instead doing this with more complex forms of data. We might want to do optimization problems. There's a vast number of solutions, and finding the absolute best solution is difficult. So we want to find an optimal solution from many different ways. We might want to do this in some probabilistic sense, trying to learn from the data of the past and make ourselves getting better and better at possible outcomes as we go through it. We might want to identify patterns in data, looking at trends, looking at scenarios, looking at relationships, and we then might want to use these patterns to predict, to classify, to actually learn from them in data as well. And this is really machine learning and being one of the biggest forms of AI. But first, to search problems. How does an AI agent choose the best sequence of actions to determine its goal? That's essentially what we're doing with searching algorithms. We're trying to reach the bottom of the graph. We're trying to find the quickest ways to actually get problems. And there's a whole bunch of mathematics really behind here to do it. And this can be taught sometimes as a mathematical problem, as a computer science problem, but it also sits within the realm of AI. Similar to constraint satisfaction problems, trying to have a set of variables, put these variables together, subjects to certain constraints, to realize something that might not be quick, might not be easy to do as humans. A simple example of this is like designing algorithms to match where people go to in hospitals, given certain conditions, given, for example, a pandemic that might have just happened, that how do we actually get people to the right resources? AI can help solve some really complex problems like this through constraint satisfaction. Operating with uncertainty, of course, is really important. Probabilistic environment. We can't expect to know all relevant information to help us form our next action at any one time. We might know the probability of specific diseases we wish to observe. We need to know the probability of their symptoms. We need to make informed decisions, maybe not quite having everything, and we need to put forms of, different forms of information together. These are just some of the small, simple examples of complex problems that AI can be solved for. But one of probably the most researched area of AI at the moment is machine learning. In fact, the two are sort of synonymous. I think a lot of people now say AI, they actually mean machine learning, or they say machine learning when they mean AI. But they are sort of one and the same. But, artificial intelligence is making machines think and act more like humans, and machine learning is just one way to achieve this. It's essentially looking for salient patterns in data. We want to learn to process data in a really effective manner, and we want patterns that can be a function of the data to help us make really important decisions. So if we want to use the patterns and go on, the way I sort of teach and think about the difference between sort of classical computer programming and machine learning is, in a classical program, you might have data and you might have rules to process this data, and this algorithm will run these rules and give you an answer. But in machine learning, we flip the paradigm around a little bit. We have data, and sometimes we have answers depending exactly what we want. And what we're actually learning in machine learning is rules to process this data, rules that can be applied to new data sources. So we want to gain knowledge about what's inherent in data, what's useful in data that can allow us to make informative decisions at certain time points. And why do we want to do this in AI? Well, one of the big reasons we want to do it is time saving. it's really difficult to write straightforward rules for certain tasks. Your simple example is, look at the slide. Inherently, we as humans know what a cat and what a dog is. Now try to describe the differences between a cat and a dog in a way that a machine could recognize it. So writing rules to do a fairly simple for us task there. So imagine when data gets more complicated, when the decisions get more complicated, when the data gets bigger, these patterns might not be obvious. They might contain useful information. We want to identify them, we want to learn them in a way that we can't necessarily comprehend. And we also want to improve, we want to make better decisions as we go through. So this is why machine learning is really useful, and machine learning in certain circumstances can be really sort of useful within healthcare. A little bit of a difference, I guess, for what I think anyway, between machine learning and statistical modeling is essentially the purpose of what we're doing. Something like linear regression gets bandied about by both people in both fields as being their own. But in machine learning, what we want to do is make repeatable predictions. So we're trying to learn something from the data for future use. Statistical modeling, we're more trying to make inferences and learn about relationships between variables. So it's just a little bit of the difference between there, how we actually assess the performance on it. In machine learning, we always think of a predictive performance, testing it on additional test data. In statistical modeling, we think of something like significance testing, robustness of model parameters, a bunch of effect sizes, these sort of things to test these relationships. So we might be using very, very similar tools. We're just using them in slightly different circumstances, which is what sort of separates out this sort of machine learning versus statistical modeling. And of course, anytime we speak about machine learning now, again, as I sort of said, the machine learning is getting synonymous with AI. Deep learning is sort of now getting synonymous with this as well. And again, people use these terms AI, deep learning, machine learning a bit interchangeably. It's essentially just sort of layers here. Deep learning is a specific subfield of machine learning, which is a specific subfield of AI. Not all AI is deep learning, but all deep learning is essentially AI if we think about it that way. And deep learning is called deep not because it's sort of meaningful, more powerful, things like that. It's essentially called deep to do with the depth of the model and the number of processing layers of information. A normal machine learning model typically probably only has one layer of processing that goes in it. We take in our data, we do one transformation to it, and we get an answer out. In deep learning, we do multiple layers of transformations to it. And through these multiple layers, multiple transformation, it generally allows us to create a more informed decision, allow us to form a better model. Of course, with that, we need more data to allow us to learn the complexities of what we're trying to solve. So it's not a case of deep learning is applicable in every circumstances. Deep learning is applicable when you have enough data to allow it to be applicable, which is a bit of a roundabout way of thinking about it. But yeah, essentially what we're doing is just transforming and transforming and transforming data so it looks less like the input and more like the output as we go through these layer by layer representations, and we just transform it and something happens. This is done by a few different means, but the main fields in sort of deep learning are what's known as a feed-forward neural network. So this is based on sort of information coming into a node, being summed together as it comes into the node, and going through some transformation as it turns out. You know, so the idea of this transformation is to learn when to turn particular outputs off or turn them on. And this allows nonlinear transformations. And this is really important in allowing us to make more modeling of fairly highly complex tasks. We can also achieve the same thing through what's known as a convolutional neural network. This is where we learn to filter data using repeatable filters and using these same filters over and over in different areas as we sort of go through it. So essentially the same thing, just set up to do a little bit different in terms of how it learns and what it learns and how it's creating the knowledge within it. The other form of machine learning is deep learning is the temporal form, the recurrent neural networks. So neural networks are designed with feedback or feed-forward loops to allow timing information to be included into the network. Modeling time series this way is really difficult. We actually put neural networks in the node of the neural networks. This is what sort of long short-term memory and gated recurrent neural networks are. the networks within networks to allow us to process very complex time information as well. So of course we need a lot more data when we're doing this, where the complexity of these systems, the number of connections essentially within these systems, and every time we've got a connection, there's something else to learn about how that connection processes the data, goes up and goes up and goes up. So we need a lot of data to do this. But why are so many people fascinated by deep learning, given it needs a lot of data? Well, it performs well when given more data. We see in things like image classification, natural language processing tasks, in speech processing tasks, such as, recognizing the words being said. Deep learning system performances are yet to sort of reach. They're very, very high, and they improve when they get more data, when more conventional algorithms tend to have a limit to what they learn and their performance with them. Of course, there's different maths and different theories that sit behind deep learning as well, saying that a single layer, hidden layer of information should contain every single processing step needed if you essentially know how big that layer should be. In practice, it's depth. It's the number of layers that really does give machine learning its power. And the other reason people use deep learning now is it takes a sort of layer of processing out. It allows us to learn in some circumstances directly from data itself, eliminating sort of a little bit of my background, sometimes a bit of signal processing that comes from, and trying to get signals ready to actually allow us to see a pattern. Instead, given that we can now do very, very nonlinear transformations, we can actually process raw data more directly. And given enough data, we can generally make a really powerful prediction with this. So that sort of ends this initial, what is sort of artificial intelligence, and a bit of a flavor, a bit of an overview of a few of the different areas. Before I move on to some of the challenges, I just want to finish up by briefly talking about a few more artificial intelligence concepts and really where current state of the art with artificial intelligence sits. So the sort of sci-fi perspective of artificial intelligence is superintelligence, having machines that are connected, able to reason and able to think well beyond our understanding and essentially dominate humans. So, it's got this form of superintelligence, and it, all the dystopian sort of images that come along with that. But superintelligence is the area of, essentially sci-fi still at the moment. For a long time, definitions of this, how to achieve this, are going to be nothing but speculation. When we move down to general intelligence, learning from experiments, learning from interactions, applying understandings to different problems, using memory, using reasoning, using knowledge, it's more achievable for a machine, more achievable, but it's still not likely in the short term. We need advances in computer processing in how we store information, particularly coming along through quantum computing, that could make this a problem. And we'll talk about this more in the issues of why general intelligence is still quite hard to achieve with AI as it currently is. So AI now is narrow intelligence. So it's specific agents built to solve a specific problem in a very specific context or domain. Systems generally solve one problem in that context, sometimes can be retrained to apply to another one that's similar to it, sometimes can't. And a lot of things that appear to have general intelligence don't. They're more likely to be a combination of narrow intelligence systems. So if you think about a voice system, it's essentially a speech recognition system to understand speech. It's then a natural language processing system to get these interactions, to understand a bit more about what's being said, to do things like queries like web searches, music recommendations, and then it might be a synthesis system to able to speak back to you. So it's a lot of very narrow AI put together to solve some particularly, more straightforward tasks. And yeah, that's really where we're at, is this idea of narrow intelligence and the idea of sort of achieving some sort of look of general intelligence by piecemealing together a lot of narrow intelligence systems. And why do we want to use AI? Why even do we want to use narrow intelligence within healthcare? And I mean, we do this because number one, data is everywhere in health systems. We collect data all the time, and AI can help us process this data. It, in theory, can help us improve diagnosis, trigger earlier interventions, discover more effective treatments. So there's a lot of things it can do. We can use combinations of classifiers, graph searching to look for treatment recommendations. We can look through data using different tools to identify candidates for possible surgery, possible paths. We can also start to piece together different narrow forms of intelligence to do virtual therapy and things like this. So we are able to look and monitor speech, voice, actions, and have a sort of agent actually do some form of sort of interaction with this to guide therapy sessions, and chatbots and things like this are all coming together to help process information. And yeah, there's a lot of really interesting research out there. But we need to also remember, despite from all the gains, there are big sort of losses. AI is really, really difficult to get right. And a lot of big companies who invest lots of money don't get AI right. Google, her image recognition has been shown in the past to be racist. Microsoft developed chatbots which learned from Twitter about conspiracy theories and Nazi sentiments. IBM had to cancel its Watson for Oncology when they realized the system continually gave unsafe advice. Amazon had recruiting software that was gender biased. Self-driving technology in Volvo struggled to deal with Australian animals such as kangaroos because they fundamentally moved different to European animals. Uber has had an autonomous vehicle strike and kill a pedestrian. Facebook has admitted that its AI system struggled to recognize the sheer variety of hate speech and illegal content in their systems. And even as early as this year, Alexa searched the internet to look for something fun to do and told a 10-year-old girl to touch a live plug with a coin. And luckily her parents were in the room at the time, which stopped that happening. So yeah, AI is very, very hard to get right. There's a lot of issues going on. There's a lot of hype. There's a lot of really cool research, but we do need to remember, and the core of this talk now is about this. There's lots of things happening that we really need to consider. And of course, I've said it a few times, data is one of the keys to AI, and there's a lot of issues and ethical concerns surrounding this. Access to data is huge. For prediction and decision models to be trained properly, they need data. And currently, large troves of data are sitting in the hands of a smaller number of larger organizations. And this stymies some research. Not all universities, not all sort of small startups can access data and access the data they need. Ownership of data is also an important ethical consider because it's linked to control, it's linked to access, it's linked to processes that come from the data. Of course, in the healthcare domain, patients generate a large variety and basically generate huge amounts of data. But then when we think about potential owners of this, including the patients themselves, these could be healthcare providers who have recommended the patient undergo a particular test, undergo a particular trial. This could be developers, manufacturers who are responsible for generating, processing, storage the data. This could be the universities setting up research studies. This, could be insurance companies who are monitoring their patients somehow. There's so many forms of ownership of data. And of course, one thing you've probably realized from these challenges I spoke about is data is biased. Data is never 100% clean and easy to use. It contains biases, and then these biases get reflected in an AI model. And clinicians really need to be trained to not only use AI, but understand how to critically assess data sources, understand what's gone into the system to understand what's come out of the system. And this is one of the bigger concerns where this knowledge gap needs to be addressed and need to be addressed quickly if we're going to put AI into clinical practice. Of course, with big data comes big computational time to actually learn from this. We need huge amount of resources. So companies who have lots of money, who may also have lots of data, have the processes to do this. But of course, being faster doesn't necessarily mean they're being more intelligent. And the other side that comes with data processing, data storage, is energy consumption associated with this, and the need to be thinking more green, more sort of global warming, and these concerns that come around training huge models to actually learn something from the data, and all the cost benefits that come along with this. And of course, the costs that come with just storing, analyzing data limit who can really achieve what with big data sources. Of course, AI, as I sort of said, narrow intelligence is just that. It's brittle, it's not very good, and we're still a long way from achieving a single general intelligence systems. And this is essentially, AI is recognizing patterns in data. It's looking at ways of processing data. You show it a new pattern, it's easily fooled. It might be able to tell you what it thinks it is, but that doesn't actually mean it is what it is. And of course, when you've got a system that is essentially looking for patterns and seeing patterns in the data, you can easily adversarial attack it. You can try to deviate the data, learn how to manipulate data to get a particular answer out of the system. And in a medical environment, this can really start to put people's lives at risk when we start to think about there's ways to fool data, that you might get a particular test, particular answer people want to give. And this might lead to certain paths of treatment and things that go along with this. So it's a very important area of things. And one of the things that really stops AI from developing general intelligence at the moment is catastrophic forgetting. When we train an AI model, it's very good at sort of doing what it was last trained to do. So if we train a system to learn about the difference between cats and dogs, it can do that very well. We then want to update it to tell horses and cattle apart. It might then start to forget all about cats and dogs and only be good at doing that next task we've sort of updated it to do. So it's not very good at retaining information over a long period of time. And I spoke about time processing earlier, and spoke about recurrent neural networks. And even something called long short-term neural networks are still very short-term neural networks. Processing data in terms of days, months, years is very difficult for machines to do. And this is why we need sort of newer forms of computing, newer ways of processing, storaging data, how to access memory within AI systems to really develop that next step of general intelligence further. Of course, AI systems need to be able to handle uncertainty properly, and a lot of AI systems don't. They know what they're trained for, and you show them a pattern and they'll be very confident, even though it's never seen the data before and given you a particularly strong answer, I think X, even though you've given it Y and it does not know what Y is. We need in medical applications and health applications to build in essentially I don't know answers, abstaining answers when it comes across data, when it comes across patterns that hasn't seen before, be able to say, oh, this is new to me, or there's some data missing, there's some bias within it, there's some too much noise within here. Pardon me, a bit of allergies there today. But yeah, we need to build in this area of uncertainty into AI agents to make them more powerful, more fit to use. And of course, coming in with this and going back again a little bit to narrow versus general intelligence, there's no one size fits all solution for AI. We can build very good individual solutions. We can make a suite of tools to put these together, but that can be costly, time consuming, and a bit messy to do. And within this, if we're only using narrow tools, the qualia, the common sense, the creativity isn't there in AI algorithms. They can only do what they're programmed to do. And if something can't be expressed algorithmically, an AI agent can't solve it. We need to, they can't think for themselves. They're only as good as the information we give them and how we set them up to actually learn. And within this comes what's known as the no free lunch theorem. The AI algorithms, there is actually no one universally good AI algorithms. Models are only as good as the assumptions they were used to create the models are only as good as the assumptions they were created with and the data used to train them. In some circumstances, some algorithms perform better, and in other circumstances, other algorithms perform better. So while There's a lot of hype now about deep learning. The problem with deep learning is it does make some assumptions on the amount of data that you have. And if you have very, very small data sets, you're not going to get a good solution from a deep learning model. You're going to have to go back to simpler models and learn this. And there's no power analysis. There's no golden rule for you have X, gigs of data, you can now use deep learning. You have Y gigs of data, you have to use this model. There's nothing like that. Unfortunately, in AI, empirical evidence is the only way for determining what is a good solution given the data that you have. So a lot of time needs to be spent training, testing models to make sure that you've got generalized solutions coming from these, not sort of a solution that's overfitted, that's very specific to the data that you use to train this with. And of course, one of the huge areas and maybe one of the biggest challenges we have concerning the use of AI and concerning the use of AI in medical applications is explainability. There is, no real way of explaining how most AI algorithms work unless they're exceptionally small, sort of shallow systems. We just don't know what's going on inside them. We call them black boxes. You feed data in, you get an answer out. We know a bit of the theory about, okay, obviously how this model was created and the assumptions around that model, but we don't actually know how it's reached a particular decision. And this is important when we try to now go, well, AI is going to take shortcuts. It's not going to learn what we want it to learn. It's going to learn a pattern in the data, and we might not even realize that pattern is there. This is known as the clever hands effect. It's learned a spurious correlation that was in it. One of the common examples used in the AI literature for this is the husky versus wolf classifier, which turned out to be a snow or grass classifier. It didn't learn the difference between a husky and wolf. It learned a difference in the context the images of huskies and wolves generally appeared in, and learned that there. There's a lot of examples if you go back and read some of the COVID-19 literature about AI and about learning from metadata attached to images and all sorts of things that in and around the sort of rush to create AI systems to help diagnose COVID-19. We did learn a lot more in and around this sort of AI systems taking shortcuts and the need for quality data when we're actually doing it. And it's also not just that we lack explainability. We currently really don't assess explainability in the right way. AI systems are often based on how accurate it did a task. And this is an incomplete description when we think about a real world task, such as medicine. You've got the flu, yes, no answer. It doesn't really tell you about treatments. It doesn't really tell you about the next way forward. So just being able to diagnose is only one part of the problem. We need to understand how that decision got reached to be able to us to plan treatments to go those next steps further. And we need metrics that not only show that AI performs well, but we need metrics, and we need to think about how we can show that AI actually brings user benefits into healthcare systems. And that's sort of really important. Instead of just thinking, accuracy, area under a curve, recall F1 score. This is very much a computer science metric. It's all about, yes, we've got a desirable model, but we're not saying anything about that usability of the model. And of course, if we continually chase a better performing model, this can have consequences. According to no three lunch theorem, we're just getting a, AI model that's really, really good at doing one particular task and one particular form of data really, really well. It doesn't actually reflect anything in the real world, and it doesn't reflect, as I said before, how can we develop models that result in beneficial change to patient care. And that's something we've got to consider as we go forward, how to properly integrate AI systems into healthcare systems. And I think it requires change from both fields. It requires pretty much how clinicians want AI to be used in the systems and how the possibilities of this, and a lot of different stakeholders need to come together to improve this performances, improve all of this, and really make beneficial change into the healthcare system. And I mean, it's not just that as well. There's a ton of health and safety in and around explainability. Models that aren't explained, we just don't know what's going on with them. There's no way of really checking they're error-free. So if we think about a self-driving car, we can see it detects cyclists, great. But if we don't have explanations there, we might not learn about how it's learned what a bicycle is. A bicycle is something that has two wheels. So this reveals that a bicycle with a side bag that's partially covering might not actually be revealed by the system to be a bicycle, and that person might get run over, might not be avoided in the same way. So we need to learn these edge cases, and the way we do that is through continual testing, but we have some form of explainability going on. And this also brings us to perhaps one of the biggest ethical concerns and one of the biggest problems currently in AI, and that is bias. So we've got bias in our data. So we could have underrepresentations of particular groups in our data. We can have bias associated with data labels. So the one particular group gets diagnosed one way, another group might get diagnosed another way. And this creates sort of insecurities that all come through and are reflected in the model. And of course, the model itself can be biased. It might not be trained well. It might not be actually able to do the job we think it can do. And interventions to improve bias is a growing area of AI research, but there's a lot of the methods still lack stability, lack generalizability, and how we build them into specific use cases and be able to use them within a healthcare system is still sort of a long way off. So, it's really important for increased explainability, not just, for a few different directions when we consider AI and AI in healthcare. Fairness. Are the right groups? No one is being discriminated against. Privacy is information being protected. Is our algorithm reliable? Is it robust? Is it causal? Is it modeling the relationship the same way every time over time? And all of these things come together. And essentially, the more explainable a system is, the more likely it is to trust it, especially if it's a system that's a bit of a black box that we feed data in and get an answer out. If it can't explain itself, it's going to be hard for people to trust it, hard for people to want to use it in healthcare education, in healthcare settings. And then in and around this, we've got a few more sort of ethical concerns to unpack. When we start to think about actually sitting an AI agent within healthcare, how do you educate? How do you do informed consent around AI systems and explain the complexities of what we've spent the last 45 minutes discussing here on different forms of AI, different forms of machine learning, different kinds of data, possible biases coming out of the machine? How and whose responsibility is it to explain all of these to patients who might be using AI or ML to make a decision about their healthcare? How do we educate doctors? How do we educate clinicians properly to be able to understand these systems, understand data, think differently to be able to reach that right decision using sort of information informed by AI agents? And how feasible is this when there's a lack of transparency in the systems and the clinician can't tell you how an AI model got reached? And when we think about issues then with informed consent, if we're moving into an mHealth world, users are now getting on their phone, getting a small AI agent, a chatbot or something, download an app, and it's got a complex range of terms and conditions associated with this. We don't have face-to-face interactions anymore. So how can we actually start to educate, inform people about AI in the right possible ways, again, to increase trust? And around this as well comes sort of decisions as we start to think about AI in healthcare applications around accountability. Whose responsibility is it when an AI-based decision leads to patient harm? Is it the doctors? Is it the person who developed the model? Is it the company that put the model in place in the healthcare system? How does all of these decisions come? And in a world where AI becomes more visible and we start to maybe get into thinking of the machine knows best, an AI agent knows best, it can interpret data better than the doctor, will doctors become afraid to override AI-based decisions? And again, how do we think about all of this when we're using black box algorithms? This need for transparency regarding data, regarding the system being used. And then when we think about current practices for sort of randomized trials and other forms of testing, are they sufficient to test the safetiness and effectiveness of AI systems now? So there's a lot of things there we need to think about, we need to consider in terms of making AI usable in the healthcare system. And of course, with this, there's a lot of other ethical concerns on a lot of things that I haven't touched. As automation gives rise to job loss, there's a need to redeploy, retrain employees. We are creating wealth by these machines. How do we distribute this fairly through these systems? How, as we change from interacting with doctors and clinicians to interacting with machines, how will this affect our behavior, our attention? How secure are these machines in storing and processing private and sensitive information? And how do we mitigate against unintended consequences, especially as we sort of go sometime in the future towards machines that learn and develop independently from what we've trained them to? So there's a lot there, and probably bombarded you guys with a lot of information, but really hope that it's been educational in terms of just a lot of different things to think about in AI. If you do have any questions that you don't get time to today, please look me up on Twitter at NickCummins41, or just get me by my KCL email. So thanks everybody, and yeah, happy to take some questions. You're on mute there, Raquel.
Today I'm muted all the day. I don't know. I'm forgetting all the time. So sorry about that. I was just saying thank you, Nick, for the fantastic talk. And yeah, I agree. There are a million things here, a lot of content and aspects to reflect about. I think from myself, at least, particularly the last 4 or 5 slides were really heavy content, heavy things to think further. We could be hours reflecting on this, on the role of clinicians, how we integrate the knowledge from the machine and the tacit knowledge from the doctor as well, so that they don't feel disempowered as well on the clinic. There are many things to discuss, but I'm going to open the turn of questions to the attendants. So please, if you have any questions, comment, I'm sure you do. So please go, raise your hand and to talk directly. It's totally fine. So yes, please, Eamon Walsh, can you ask, please? Thank you.
Yes, hello, thank you. I really enjoyed your talk. When you were talking about trust at the end, I was thinking of the supermarket checkout. So in the supermarket, you have a choice sometimes between a human or a machine, and even all other things being equal, a lot of people, including myself, often goes to the machine. It depends a little on my mood. It's not got to do with trust. I think I trust them both equally. I think they'll get the price right. But is there anything that you're aware of, where not just trust, but where people sometimes prefer a machine over a human for certain types of transaction?
I know of I spoke about it very sort of in the middle of the talk, the virtual agent for therapy. And yeah, the research in around that was quite interesting. It was developed as a DARPA project for the US Army. And what they found was that the returning soldiers were more comfortable talking to the virtual agent, where they felt less judged. So even though they knew they were being judged because they had this screen in front of them showing all these readings that were happening on their, their voice, their facial actions and all of this, they felt more comfortable because it was a machine, it wasn't a human. So they were able to open up to it more. So it does give you just that glimpse of, that there are certain times where people aren't going to be naturally vulnerable or naturally open up, and the machine might help with that.
Interesting, thank you.
Thanks for the question. So I'm going to read now a question from the chat. This is from Mian Haider Ali. So Mian is asking how we can make AI more easy for those who don't have the knowledge and cannot even code, because you want to generate trust by making clinicians understanding AI, but that's not straightforward at all. So how can we get that?
I mean, I didn't sort of go into that so much here. What is an explanation comes into multiple levels of this. you know, if I went to a doctor and they offered me an AI test, I'd be there for 5 hours asking questions on the AI and the explanations I want from it. They might be very different from someone with no experience with AI who wants something from the machine. And I've seen sort of from research coming from RADAR-CNS that we think about feedback that people might want from apps and might want from things. Everybody does want something slightly different. And I know I'm not really answering the questions there, but it's more that, yeah, your point here is that, yeah, how to make AI understandable for people who don't have those knowledge. I think it comes from needing to teach things earlier, sooner, and, you know, AI, maths, and thinking about these things should be fundamental part of health courses going forward. Is the only way we can do that. We just need to be working as data scientists closer with clinicians. So yeah, and of course, yes, our wonderful course that Daniel has pointed out, and hopefully soon to be short online version of it as well that will help people.
And probably including this in the educational programs from the doctors and clinicians, maybe from before. Maybe not at the level of the programmer or, you know, a computer scientist, but maybe something introductory could help as well. Yeah, well, and there was one hand raised by Julie Munga. I don't know if you want to ask still, or was your question already answered, Julie?
Yes, I'm here. I'd like to say, Nick, thank you very much for this very interesting talk. I have 2 questions. One of them is, what sort of mechanism do we need to put in place to ensure accountability of AI? And also, what can be done to support the auditability of AI?
I think both questions is there's no simple answer at the moment, and I might have said, oh, we just need to do this, but I think just need to do this is something where we just again come back to needing greater interactions between data scientists, clinicians, and different understandings of, you know, I know when I speak to my statistician friends, my more clinically focused friends, my more data science focused friends, we think about data such different ways, even if we're operating on the same data set sometimes, that these common languages and common things need to be addressed. And through more sort of stakeholder engagement as we develop AI and try to embed AI into systems, these answers are going to become clearer.
Thanks very much, Nick. Thanks very much, Julie, as well for your questions. Is there any other common questions? I can't see any hand raised now, but anyone else would like to make a comment or ask anything else to our speaker today? Oh, Daniel. Yes, please go.
Nick, a great talk, of course. You said a lot of trust of there might be a lack of trust of AI or machine learning prediction modelings. But what I also notice is that what happens if the machine might predict better, but the clinician doesn't trust the machine and makes the wrong decision. I think nobody really talks about this problem, and it's a very difficult topic. So because
yeah, it's something I was reading on this afternoon. I think there was one point in the slides there where it's who's accountable when a doctor overrides a machine, and then if doctors continually override machines, and in the case where the doctor gets it wrong, is that then going to feed these biases back into the systems as well? So how, it's again a minefield of things that, you know, we need to unpack. And you know, why working somewhere like King's at IOPPN and even in our department is so cool, because we get so many opportunities to try to push forward these, like the translational side of AI a lot more.
At the end of the day, I guess the question is who holds responsibility on this?
Yeah.
I think
the machine cannot hold responsibility, right?
I think, I mean, more regulations are coming through either the EU and hopefully will be adopted through into Britain as well. And responsibilities and things are coming, and things are getting more regulated, but I guess as things get more embedded, more problems are going to come up, and yeah, exciting times really ahead.
Totally. It's difficult to be optimistic, to be honest. After the talk, I was thinking, how can we be optimistic? Maybe a final message to finish the talk. So how can you think, or what are, I don't know, the ideas that you can leave for us to say, no, there's some optimism related with what we are doing?
Look, there's a lot of exciting research happening and a lot of really cool results coming out. One thing I think more immediate that we need to do is work together with clinicians to make sure we're solving the right problems together, and make sure that, I mean, both AI practices and clinical practices need to change together to solve this problem. And I think that's really exciting and really huge opportunities coming from there. And while we're doing that, we just have to be having these other discussions. They're definitely not meant to scare people. It's meant to just be this sort of, there's so much to think about going forward. But the opportunities and the research shows the power of AI. We've just got to get it right.
Great. So we will leave it here then. If there's no other comment or question, I think with this very positive message from Nick. Thanks very much to our speaker, Nick. It was great having you with us, so thanks very much. As he said, if you have any further questions, you can reach him on Twitter or by email as well. And this presentation will be shared on the prediction modeling group site. So if you want to listen it again, you can watch it again. So you will be able. So from us, that's everything. Next month we will have another talk on prediction modeling and machine learning. We will advertise it in due time on Twitter as well, and our regular ways of doing so, by email as well. And I hope to see you here next time again. So thanks very much and enjoy your evening.
Thanks, everyone.